Hey everyone, welcome back to Math 251 and congratulations. This is the last lecture video that you have to watch. This is the very end of the term, so give yourselves a pat on the back. I know that I have had so much fun with you guys this term, and if you're not in my class, then I'm sure your instructor has as well. So great job, and let's get right into this video. In this last lesson, we'll be talking about how to sketch a graph of a function. We have learned quite a bit about functions and what the first and second derivatives tell us about a function. So we're going to put all of that together in this lesson and bring it all together and sketch a pretty accurate graph of some functions. This problem solving strategy is from the textbook, and it kind of just lays out the steps that you should take with these kinds of problems, how to go step by step and get all of the information we need. So first, we need to determine the domain. Second, we locate the x and y intercepts, and then we evaluate the end behavior. This end behavior just means the limit as x goes to positive infinity and negative infinity of f of x. So that is what end behavior means. If it's a rational function, then we will have to find the degree of the numerator and the denominator and go from there. In this example that we're going to be doing here, we don't need to worry about that so much, but we do have other strategies for determining the end behavior of some functions. Then we determine if f has any vertical asymptotes, and then using f prime and f double prime, we determine critical points, increasing, decreasing, local max, local min, and concavity, and inflection points. So we have a lot to find about these kinds of functions, but as long as we break it down into these steps, it should be no problem. So in this example, we want to sketch a graph of the function f of x equals 2x cubed minus 6x plus 3. And just for brevity's sake, I gave you the zeros in this problem. So our first step, step number 1, is to determine the domain of the function. This is just a polynomial, so we don't really need to worry about any vertical asymptotes or holes or anything like that. The domain of this function is negative infinity to positive infinity. So step 1, our domain is negative infinity to positive infinity. You might also see this as all real numbers. All right, that is pretty easy. Step number 2, locate the x and y intercepts. Well, I already gave you the x-intercepts, right? So we have that the x-intercepts are at, negative 1.90, 0.560, and 1.390. What about the y-intercepts? Well, the y-intercept is when x is equal to 0. So if I plug in 0 into my function, f of 0, this is 2 times 0 cubed minus 6 times 0 plus 3. This gives us the point 0, 3. So these are my x-intercepts, and I just have the one y-intercept. All right, that is step number 2. Step number 3, I want to determine the end behavior of our function. We're going to talk about this a little bit at the end of this lecture video if we don't just have a polynomial like we do here. But remember that to find the end behavior of a function, we have to look at the leading term of the function. In this case, we have a cubed function, and it's positive. So if we think back to our college algebra days, a cubic function that has a positive coefficient has this sort of shape. So that means that the limit as x goes to negative infinity is negative infinity. The limit as x goes to negative infinity of our function is negative infinity, because as we get really big in the negative direction in the x-axis, we also get really big in the negative direction in the y-axis. And the limit as x goes to positive infinity of our function is positive infinity. because as we get really big in the positive x direction, we also get really big in the positive y direction. Next, we need to determine if our function has any vertical asymptotes. In this case, since it's just a polynomial, we do not have any vertical asymptotes. But if you had, say, a rational function, so a function on top of another function in a fraction, then to find where the vertical asymptotes are, you would set the denominator equal to 0. Set the denominator equal to 0. Wherever our denominator is equal to 0, those are the x values where we have vertical asymptotes. Okay, now we need f prime and f double prime to find all of the other interesting things about our function. So to find f prime, I can just use the power rule here. So f prime of x is equal to 6x squared minus 6. And I need to find a lot of information using this derivative. I can find increasing, decreasing, and local extrema. So first, I'm going to find my local extrema by setting f prime equal to 0. This gives me 6x squared equals 6, or x squared equals 1, which gives me x equals plus and minus 1. So plus and minus 1, these are my critical points. Critical points where I have local extrema. I don't know if they're maxes or mins yet, but when we find our intervals of increasing and decreasing, that will tell us where we have a local max and where we have a local min. So from here, to find our intervals of increasing and decreasing, I'm going to plug in our critical points onto a number line. So I have -1 and +1. And I'm going to pick a point in each of these intervals as we've been doing all term. I'm going to pick -2, 0, and +2, and plug each of these test points into f prime to see if we are positive, which means that our function is increasing, or negative, which means that our function is decreasing. So plugging in -2 into f prime, I get f prime of -2 is 6 times -2 squared minus 6. This is 24 minus 6, which is positive 18. That means that our f prime is positive, or that our function is increasing on this interval. Next, I have f prime of 0, which is equal to 6 times 0 squared minus 6, which is -6. That means on this interval, our derivative is negative, or our function is decreasing. And finally, what is f prime of +2? This is 6 times 2 squared minus 6, which is positive 18 again. So what we have just determined is that our function is increasing on the intervals from -infinity to -1 and +1 to infinity, and we are decreasing from -1 to +1. We can also use the first derivative test here to determine whether we have a local min or a local max at our two critical points here. So we can see here that we are increasing on this side of -1 and decreasing on this side of -1. And then we're decreasing here and increasing here. This tells me that I have a local max at x equals -1 and a local min at x equals +1. We are almost there. We have gleaned a lot of information from our function so far. The only other thing we have to do is concavity by finding the second derivative. So our second derivative here, f double prime of x, is equal to 12x. And I set this equal to 0 to find our possible points of inflection. Of course, this just gives me x equals 0. So this is our possible point of inflection. And to find our interval of concavity here, I again set up my number line, plot our point of inflection, and I pick a point on either side of it. Let's pick -3 and +3. This is f double prime. So f double prime of -3 is 12 times -3, which is -36. That means that we are concave down here, and f double prime of +3 is 12 times +3, which is +36. So we are positive here. So this tells us that 0 is in fact a point of inflection since we change concavity. And this tells us that we are concave up from concave up from 0 to infinity, and concave down from -infinity to 0. All right, and now is the moment that we have been waiting for. We can finally plot our graph. We have we're going to have a very good sketch at the end of this since we have so much information about our graph here. So the first thing that I like to do is draw some arrows to remind me of what my end function or my end behavior is going to look like. So remember, this is a cubic function with a positive coefficient, which means that I'm going to have end behavior that goes to infinity as x goes to positive infinity, and negative infinity as x goes to negative infinity. So I like to draw my arrows first. Next, I'm going to plot my x-intercepts. We decided that we have x-intercepts at -1.9, 0.56, and 1.39. So let's draw those here. This is the point -1.90. Sorry, I already forgot what I said. 0.56, 0, and 1.390. And we have our y-intercept here of 0, 3. So we have end behavior, we have all of the points that we have. Let's go ahead and sketch or draw in our local max point and local min point. So we know that we have a local max. We decided at x equals -1. So that means that we'll be somewhere right over here. This is x equals -1. And we have a local min at x equals +1. This is a x equals +1. And now we can pretty clearly see the shape of the graph coming along here, right? So let's go ahead and sketch this shape, and then we can fill in some of the details or double check to make sure that this looks right. So I have let's see, I'm not really good at drawing these kinds of graphs, but we'll go for it. So we have this shape. Oh, okay, that's not so bad. All right, so we found our point of inflection to be 0. And it's, kind of hard to tell on here, but this makes sense, right? We're changing from concave down to concave up here at this point, x equals 0. We can see that this is a point of inflection. And we are increasing from -infinity to -1, decreasing from -1 to infinity, -1 to +1, and increasing again from 1 to infinity. And of course, we have our critical points at -1 and +1. So I'd say that this is a pretty good sketch. If we wanted to find the y values for our two critical points here, we could, of course, plug in x equals 1 and x equals -1 into our original function to see what the y values for these particular x values are. I do want to talk briefly about end behavior. In this graph, we had pretty easy end behavior since we just had a polynomial. But if we have a rational function, then it's a little bit trickier. So let's talk about rational functions. Our textbook gives us a pretty good hint here. So if we have a rational function, f of x equals p of x over q of x, where the degree of the numerator is greater than the degree of the denominator, then f can be written like this. So basically it's telling us how we can get the end behavior from a rational function, but we have to look at the degree of the numerator and the degree of the denominator in order to find the end behavior of a rational function. If the end well, let's go through some examples. So if, for example, we had f of x equals, f of x equals 2x cubed minus 3x divided by 4x to the power of 4 plus 6x. Here, our degree on the top is less than the degree on the bottom. When we have a degree on top that is less than the degree on the bottom, then this means that we will have a horizontal asymptote. Horizontal asymptote. Usually this occurs at x equals 0. Sorry, y equals 0. But when the degree on the top is less than the degree on the bottom, then we have a horizontal asymptote, which means that the end behavior will go to a constant as x goes to positive and negative infinity. If we were to switch this around and say f of x equals 3x to the power of 4 minus 2x divided by x cubed plus 5x, here our degree on the top is greater than the degree on the bottom. And when the degree on top is greater than the degree on the bottom, then our end behavior, we go off to positive or negative infinity. Positive or negative infinity. It just depends on the sign of our function. So here, these are both positive. So anyway, I'll let your instructor go through some more examples of this end behavior because it is kind of a case-by-case thing. But just remember that we have to look at the leading term on the top and the leading term on the bottom. All right, that's it for now. Congrats again on making it through this course. I hope you have a wonderful break, and maybe I'll see you later. Bye.